what I wanted to cover today was effectively the in-class assignments that went along with the lectures that you guys watched the video for because I was ill. So let me just pull those open real quick. And answer any questions about that content that you guys may have.
Yeah, what are the equations? That's all I need.
So, oh, that's what it's not doing. Sorry. Where's Dropbox up in this bitch? Here we go.
So just real quick, in the event that we do not have class Thursday,
Mhm.
we'll do some kind of Zoom thing because you like to report them, or
So technically it depends. Okay. So if I'm told that classes are canceled for Thursday, then we are not doing anything because classes were canceled. If classes are not canceled Thursday, then we will be having a class, whether that's on Zoom or here in person, depends on whether or not they tell me to stay home or not. So if they tell everybody to stay home, but classes are not canceled, then we will obviously be over Zoom. Yeah, I was definitely, the first thing I did when I woke up yesterday morning was look for an email that said something about winter weather and not having class. But didn't get that lucky. Yep.
Thursday. I'm sorry with Thursday. They're pushing.
All right. Okay. So let's talk about things. Okay. So this particular problem was associated with a lecture where we were learning about the effects of having non-linear core materials. So I gave you guys a handout. So here's the class 4 handout. You guys should have a physical copy of this in front of you and all that kind of stuff. I'm actually going to zoom out of this a smidge just so that we can kind of look at things a little bit easier here. So this is a magnetization curve that I pulled from a particular textbook for M1929 gauge steel sheets and then a soft steel casing. So what's pretty important here when we're looking about this graph, looking at this graph, is effectively noticing that the relationship between B, which is on the vertical axis, and H, which is on the horizontal axis, isn't linear anymore, which means that our relationship that B is equal to mu H now kind of changes depending on what our H value is. So it's not going to be a constant. We're going to have to look at our particular tables to figure out where along our operational curve our effective circuit exists so that we know what the magnetic fields are doing, okay? And these are going to be different curves for different types of materials. So if we look at the back page here, this is a similar BH curve where once again, B is on the vertical axis and H is on the horizontal axis. And we can see that there's a vast difference between the behavior of a nickel iron alloy and cast iron. So the type of material that we choose for our core is going to greatly impact the behavior of our system. Okay?
Like, was that ever a thing where they would actually use from the cast iron inside of one?
Oh, absolutely.
Really?
Yeah. Because it's incredibly highly magnetic. So it stores energy incredibly well.
I looked at it based off of like, I interpreted based off of just like, oh, this one all the way up here, so this one obviously better.
So
Nickel is definitely not enough, so.
yeah. So realistically for the application, this is slightly getting sidetracked, but if we're wanting to do things at lower frequencies, so transmission frequencies of 50 and 60 hertz, so for power applications, we probably want a ferromagnetic core because it's very easy to magnetize and all of that kind of good stuff. But if we were trying to do stuff at radio frequencies or microwave frequencies, we would probably want a ceramic core, which isn't particularly magnetic because we will lose a lot less energy in that case. So that's why choosing the core material for the application is incredibly important. And these tables are helping us kind of understand what those choices might look like and how to read these tables and use them for, hey, if I'm only able to supply a specific amount of current to the system, what should my expected magnetic flux densities and stuff like that be? How is that going to impact things like reluctance, all of that kind of good stuff? All right, so in this first problem, we're told that the magnetic core is made of nickel iron alloy sheets with a stacking factor of 0.95. So just again, to recap some stuff that should have been covered in the videos, don't know whether or not you guys watched them, that's your bag of cats. Stacking factor is effectively a measure of how much of your core is actually the core material, and the remainder of it is some type of insulation. So effectively, our cores for magnetic circuits are very often made of very thin laminated sheets of ferromagnetic material separated by insulators. And the reason that we do that is so that we don't have large, what are called eddy currents propagating around our system, because those large eddy currents are going to accidentally induce magnetic fields that are in the opposite direction and will tend to damp down our system. So we mitigate the effects of eddy currents by breaking up our ferromagnetic material into smaller sections so that the current can't ever get big because it can't can't flow through those insulating layers. So stacking factor is just a representation of how well, like how much of our core is the actual material versus how much is insulation so that we can mitigate eddy currents propagating through things. Okay. All right. So we've got our magnetic core material with an air gap, nickel iron alloy sheets with a particular stacking factor. The thickness, so that's the dimension into the page for this guy, is 4 centimeters. Okay. We are intending to estimate the amplitude of the AC current needed to sustain a maximum flux density of 1.4 Tesla in the core. So the first thing that we're going to need to figure out is what value of H corresponds to a flux density of 1.4 Tesla. So if we look at our sheet here, let me see if there's a way I can rotate this. I'm sure there is. I'm just dumb and I don't know what it is. All right. Well, we won't worry about it then.
Not so cool when you just put your thing in landscape, put your entire computer in landscape. Or you already are in landscape.
All right, we'll just deal with this. Okay. So our B field was 1.4 Tesla. So what I'm going to do here is I'm just going to draw a line along this 1.4 Tesla thing until I intersect with the nickel iron alloy line, which is right here. And then from that intersection, I'm going to draw a line down. And that's going to tell me what the corresponding H field is. So it looks like it's somewhere halfway between whatever these two lines are. So we're just going to make an estimation based on that point. So to me, this looks to be halfway between 400 and 600. So we'll use 500. Okay. So I even make a note here. It's 500 from the graph, but we found our core to be, 500 amp turns per Weber. No, actually, let me look at the units of that. Might be amp turns per meter. Thank you. Okay. So our ultimate goal here is to figure out current. Okay. So this is a very similar problem as to what we've been solving previously. So we're going to use those relationships. We just effectively no longer have our relative permeability given to us. So we're going to have to extract that from the information in our graph. So going back to those previous relationships, what were the relationships that we were using before the break and all of that kind of stuff, right? So we had some relationships for, I want to say, so let's see, our Ohm's law, MMF, which was the same thing as NI, if I'm remembering correctly, right? So that's V is equal to I, which in this case is our flux, times our reluctance, right? So if our ultimate goal here is to figure out I, and I'm going to write it as a capital I, even though we're finding an AC current, that might be best done as flux density phi B over reluctance divided by our number of turns. Does that seem like a reasonable way to calculate I based on everything else we've done? Okay. So then that begs the question of how do we find phi B? How do we find reluctance? And how do we find N? Well, N is 100, it's given to us. So we don't have to do any work for that at all. What about phi B? Exactly right. Okay. So phi B, our flux, is just our B field in our core times the area of our core. So let's do that down here. So our B field was given to us as 1.4 Tesla. And then our area, so our flux path, if I just draw our flux circulating around this thing, and I'm going to assume it's going in this direction, like so. So we're just looking effectively for the cross-sectional area of our core, right? Well, our width is 5 centimeters and our thickness is 4 centimeters. So 5 centimeters times 4 centimeters. And we probably need to do a conversion factor as well. So a Tesla is a Weber per, actually. So we're going to use our stacking factor. Yes, you're absolutely right for our area. Thank you. So let's put the 0.95 as well. So let me just annotate this really quickly. So this is our width. This is our thickness. And if we have a stacking factor, absolutely yes. It should always be integrated in there because it's effectively telling us how much of our core is actually core material, right? So that is very much going to impact our cross-sectional area because not all of our core is the actual core material. So thank you for that there. So our conversion factor, let me go through this again. So I'm going to have 1 Tesla in the denominator. This is 1 Weber per meter squared. So now I should have 100 centimeters per meter. Square that guy, and let's just look at things really quickly here. So this Tesla cancel this Tesla. I have centimeters canceling these centimeters. I have these meters canceling these meters. The only thing I'm left with is Weber's. So this seems fairly legit. Let me grab a calculator here. All up here. So let's see, and you'll need one copy of each of the 3 sheets.
Oh, okay, so 1, 2.
Yep. You already good? What's,
Oh, is it that one?
all right, so throwing this into my calculator, 1.4 times 5 times 4 times 0.95 divided by 100 squared. So this came out to me to be 133 over 50,000, which I'm obviously not going to leave it in that. 2.66 milliwebers. Did anybody else get that? Okay. Owen's not here to correct me on adding or forgetting the correct number of zeros, so is milli the correct prefix there? Good deal, okay. All right. So we've got our phi b taken care of, we've got our n taken care of, so the only thing that's really left here is our reluctance, okay? So this should be fairly straightforward because our core has a uniform thickness, right? So we're going to have the reluctance of our core added to the reluctance of our air gap will wind up being our total equivalent reluctance for our circuit. Everybody okay with that? Okay. All right. So just as a quick reminder, because it's been a couple of weeks for me and for you guys, how do we find reluctance again? So in general, reluctance is length over permeability times area, right? Okay. So for our core, what is our length going to be? Okay. So I don't think it's going to be, so let's write this out kind of formally here. Okay. So let's start with this section right here for our flux path, right? So what is the length of this line? 30 minus 5, I would think, right? Because 30 is the length from the outside to the outside, but then we would subtract half a W from this side and half a W from this side, so it's just going to be that length minus W. So 30 minus 5 looks like 25 centimeters, right? And then we've got, exactly right, another 25 centimeter part right here. What about this guy right here? Yes. Right here. So the inside distance is 20, and then we're going to add half a W on both sides. So that's 20 plus 5. So it's the same thing as 25. And then over here, exactly right. So it's going to be 25 minus 2 is 23 centimeters. So in total, just doing simple math, this is 100 minus 2 is 98 centimeters. Seem reasonable? Okay. So we have 98 centimeters. All right, so now we need to figure out what mu is. Well, we haven't done that part yet. Anybody have any thoughts on how we might do that? So I want us to recall that B is equal to mu H, right? We have H and we have B. So from that, we should be able to calculate mu. Now notice, I want to do something really quickly here. Usually, mu, the way that we've been doing it, has been our relative permeability times the permeability of free space. That is not what we're going to do here because we don't need to. If we have B and we have H, the ratio of those is just mu with all the right units and all that kind of stuff from the jump. We don't need to do anything else, okay? So just as a quick aside here, mu is going to be, for the core is going to be the magnetic field in the core divided by the H field in the core. So that is 1.4 Teslas over 500 amp turns.
2.8 times 10 to the negative 30.
So let's look at those units really quickly, okay? So 2.8 times 10 to the minus 3 somethings. So right now this looks like Tesla meters per amp turn, where an amp turn is the same thing as an amp because a turn is a unitless quantity. Okay. So I'm just going to come down here at the bottom and we'll wind up erasing this in a moment. So we have Tesla meter per amp turn, and I'm just going to throw away the turns because they don't really do anything. What is our normal unit for our permeability? Look in the previous problems that we've worked. What units did we give it? I genuinely don't remember at the moment because it's been 3 weeks. I feel like was it Henry's per meter or did we do Henry's per centimeter? We usually did centimeters because our lengths were usually in centimeters, right? So our ultimate goal over here is to get it into Henry's per centimeter, okay? Well, a Henry, for what it's worth, is 1 volt second per amp, which is the same thing as 1 Weber per amp. Well, a Tesla is a Weber per meter squared. So if I replace this guy with a Weber and then I put meters squared down here, this meter cancels that guy. And so I have Webers per meter per amp. So I'm really close to what I need from the jump because a Weber per amp is a Henry, okay? So realistically, so I could call this thing right here Henry's per meter and be fine. So what do I need to do to get it into Henry's per centimeter? Right. So this would just be whatever this thing is. So that would be times, divided by 100 centimeters per meter would give me Henry's per centimeter. So if we had 2.8 times 10 to the minus 3 Henry's per meter, then this is going to come out to 2.8 times 10 to the minus 5 Henry's per centimeter. Are we okay with the manipulation we've done to units there to make sure everything's on the up and up? So a Henry is a Weber per amp. So here, when I had Webers over amps, I just called that a Henry. So just to be, 1 Tesla is equal to a Weber per meter squared, which we use that conversion right here in a previous step. Let me run through it again. All right, so let's go with what we started with, okay? So we initially started with a Tesla times a meter divided by an amp times a turn. Are you okay with that? Okay, so the first thing that I did was I threw away turns because that's a dimensionless quantity that doesn't mean anything. Okay. Okay, so now what I'm going to do, I'm doing this more formally, I guess. I'm going to put a Tesla on bottom and then a Weber per meter squared. So that's me converting from Teslas into Webers. Are we okay with that? All right. Now, I know that a Henry is a Weber per ampere, so I can write that as 1 Henry ampere over 1 Weber. And so if I start crossing things out, I can see that the Tesla cancels the Tesla, the Weber cancels the Weber, the amp cancels the amp. This meter cancels one of these meters. So I have things in Henry per meter. So lastly, I'm going to have this as 1 meter is 100 centimeters, where this meter cancels this other guy. And so ultimately, the units I have here, I had originally, I simply need to divide that by a factor of 100 to get it into Henrys per centimeters. So Zach originally told me that it was 2.8 times 10 to the minus 3, what was effectively Henrys per meter, which turns into 2.8 times 10 to the minus 5 to give it in Henrys per centimeter. Is that clear? Okay. So down here, we would put 2.8 times 10 to the minus 5 Henrys per centimeter. And then our area, which WT times our stacking factor, right? So 5 centimeter, 4 centimeters, 0.95. Kind of wish I had just found out what the area was earlier, but that's okay. So if I throw this into my calculator, I have 98 over 2.8 times 10 to the minus 5 times 4 times 5 times 0.95. And I wound up getting 1.842 10 to the 5, right? Amp turns per Weber. May I erase this dimensional analysis at the bottom of this page? Okay. That's what the video is for, so you can pause it. Or the video will be for once I get off my ass and put it up. All right, so how do we find the reluctance of the gap? Very similar approach. What is the length of our gap? I believe it's 2 centimeters. What is the permeability of our gap? So it's just air, right? So 4 pi times 10 to the minus 9. Henrys per centimeter. And then what is the area of our gap? So typically speaking, what do we do to find the area of our gap, right? We add the gap length to each of the dimensions of our core, right? So that's just going to be 4 plus 2 multiplied by 5 plus 2. So 7 centimeters by 6 centimeters. And I'm just gonna make an annotation down here. So this is W plus LG, and this guy is T plus LG. Do we need to include our stacking factor in our gap reluctance? No, because it's just air, right? So throwing this in my calculator, I have 2 over 4 pi times 10 to the minus 9 times 7 times 6. Syntax error, screw you. 2 over 4 pi times 10 to the minus 9 times 7 times 6. 3.789 times 10 to the 6th amp turns per Weber. That looks too much like an M for me. And adding these guys together, so 3.789 times 10 to the 6th plus 1.842 times 10 to the 5 gives me 3.973 times 10 to the 6th amp turns per Weber. And we now should have all of the constituent parts to put into our expression in order to find current, right? That is correct. So I will happily annotate that as mu naught, because that is exactly what it is, Brock. So from here, our current I, or at least the magnitude of our current I, is just our flux times our total reluctance divided by our number of turns. So that is going to be 2.66 times 10 to the minus 3 Webers, because I had milliwebers. Our reluctance was 3.973 times 10 to the positive 6 amp turns per Weber, all divided by 100 turns. And just for the sake of argument, if we look at our units here, Webers cancels Webers, turns cancels turns. So the only thing that we have left is amps. And if I throw this into my calculator, 2.66 times 10 to the minus 3 times 3.973 times 10 to the 6, all divided by 100, comes out to be 105.682-ish amps. So other than the little bit of extra legwork about figuring out what our permeability for our core was and figuring out what our air was, our core area was by having to take into account the stacking factor, the bulk of this was very similar to what we had done previously, but it's actually more close to what we would see in a real life material that is non-linear core. Okay. All right, so how do you guys feel about this one? Nothing too particularly wild or crazy. So now we'll move on to ICA problem number 4, which is the one that you guys traditionally hate with a passion. where the H came from? Okay, let me, give me just a moment, please, Brock. All right, so to answer your question, Brock, we were told in the problem statement, and let me find it specifically up here. We are trying to estimate the amplitude of the AC current to sustain a flux density of B is equal to 1.4 Tesla. And we were also told that our core was made of nickel iron alloy, right? So I looked at my table and I just drew a line from 1.4 Tesla on my B axis until I hit the curve for nickel iron alloy. And then I use that to find the value of H that is corresponding to that B of 1.4 Tesla, which we estimated to be approximately 500 amp turns per meter based on the graph. So just for what it's worth, if instead our core were made of medium silicon sheet steel, we would have used 1,000 amp turns per meter. If instead it was made of soft cast steel, we would have used about, let's call it 2,200, just based on the graph. So the material that is used for our core influences the value of H that we have to supply, and therefore the current that we have to supply in order to maintain that level of magnetic flux density. Okay. No problem. All right. So ICA number 4. So we are asked to determine the mutual inductance seen between windings B and C of this particular magnetic circuit. Okay, so winding A doesn't really have anything to do with what we're doing, so we can largely ignore that. So one thing that I want to note here, and I think I talked about this a little bit in the lecture or whatever, but the directions of our flux very much matter here, okay? So if we look at the winding direction for coil B, okay, so this is what's gonna wind up telling us our sign at the very end. The way that it's wound and the way that the direction of the current is flowing, my thumb should tell me what direction my flux is. So since my winding is wound around the front and around the back, my thumb is pointing in the direction of flux. So this guy is generating flux in this direction. Then it's going to flow up through here. Some of it's going to split off and flow down through this guy and return this way. Some of it's going to split off and flow down and flow through coil C in this particular direction. If I were to map out the direction of flux for coil C, for what it's worth, based on the direction the current is flowing and the way that the coil is wound, I'm going to do this one in dark blue. So it should flow in the same direction as our flux from coil B. So the reason why I'm making note of these directions is because that's going to tell me what the sign for my mutual inductance is going to be. Because the arrows are pointing in the same direction, we should expect our mutual inductance to be positive. If our flux arrows were pointing in opposite directions, our mutual inductance would be a negative quantity because the flux paths are opposing each other, okay? So this is just a quick check to figure out what sign I'm going to wind up having at the end. So I'm just going to make a simple note here. M should be positive based on the direction of our current flow as well as how our coils are wound. So before we move on from this concept, is everybody okay with that?
Do we need to worry about A?
So not for this one in particular, because we are not using it for anything else,
Okay.
right? So I believe, yeah, so we're just worried about B and C, so coil A could not be there at all, and it wouldn't make any difference whatsoever for what we are doing. I believe in the video lecture for this, I worked out the mutual inductance between, I think it was A and B as an example. And for that one, the mutual inductance came out to be negative because of the direction that A is pushing flux around the circuit. Just for the sake of argument, I'll do that one in purple really quickly, right? So A is pushing flux up, and then it's going to split and flow this way through B, and it's going to split and flow this way through C. So we could see that the mutual inductance between coils A and B would actually be negative, whereas the mutual inductance between coils A and C would be positive based on the direction of flux flow. Brock.
Why do ones like branch off of that first intersection?
It does.
That broke off.
Let me,
Why does E not go up?
okay, so it totally can and should, so let me redraw that. Yeah. So starting here. Okay, so no, I see what you're saying and you're absolutely right. So it should flow up like so. Cross like so, up, up. These guys are going to add together to form back there. You're right. Okay. So that means the mutual inductance for A and B are still negative. A and C, so let's see. A and C is still positive. Yeah. All right. But thank you for that, Brock. You were correct. All right. So we've got our sign on our magnitude. So now we need to figure some things out here. Okay. So whenever we're calculating mutual inductance, and I feel like an idiot for not bringing my notes because I'm gonna have to do this from memory, but it'll be okay-ish. We always have a choice to make because the mutual inductance, if we calculate it as the flux generated by coil B passing through coil C, it's going to give us the exact same answer as the flux generated by coil B that's passing, generated by C that's passing through B. So we effectively just need to choose which one is going to be our source and then work the problem. So we have a choice as to whether or not we want to consider B to be our source or C to be our source. Brock.
So, similarly, treat this like electric circuit.
Extremely similarly, like 100% similarly. So this is kind of like a superposition style problem. I don't know how familiar you guys are with the superposition principle, but that's a method of analyzing a circuit with only one source on at a time. And that's effectively what we're going to do here, where we're just going to treat either coil B or coil C as the source for our circuit and figure out how much flux is flowing through the other coil.
Is that why it's MBC equals MCB?
Yes. Because we'll get the same result regardless of if we choose coil B as the source or coil C as the source. So arbitrarily pick coil B or coil C to be our source for this thing. B. Okay, so B is going to be our source. All right. So I'm going to draw this as a circuit. And recall, coil A has nothing to do with the calculations that we're about to do. So I'm not going to bother even drawing that in the circuit at all. All right. So as a magnetic circuit with coil B as our source, we might have something that looks like this. Okay. So here is my source. So this is MMFB. This is going to be the reluctance of my left branch, okay? So just as a quick aside, I'm going to do this flux path in blue. So this is the total flux path for the left-hand side, and I'm going to make a note here, and I'm just going to put left, okay? Now I'm going to come and I'm going to do my middle path. So I'm just going to call that R mid, and I'm going to throw an R gap in series because there is an air gap through that path. So here is my mid, so it's in purple. And then for what it's worth, I'm going to do gap in green. And then I'm going to have my right hand flux path and its reluctance. Exactly right. And we're not going to put the C coil on here because we're not interested in what C is producing. We're interested in the flux that's flowing through C if it were off, because we're talking about mutual inductance. So we chose B to be our source, which means we're turning C off, and we're interested in the flux that flows through C, or realistically, the flux that was generated by B that flows through C. Okay. So let me draw this just really quickly before I get more distracted. Let me do this one in orange for what it's worth. So this is our right path. And so realistically, what we are interested in, because I feel like this is what your question was about to be, is we are trying to find this flux here, which I'm going to label phi BC. So that subscript means it is the flux generated from coil B that is flowing through coil C. The fluxes won't be the same, but the inductances will. So the fluxes, it's practically guaranteed that they will not be the same. But the inductances will, because the way that the ratio of the reluctances are going to work out effectively is going to force that to happen. So we could work this problem the opposite way after we finish it up one way and prove very easily that we're going to wind up getting the exact same result. So that's why our choice is completely and utterly arbitrary. Um, a kind of hand wavy way to explain why it has to happen that way is that energy has to be conserved in our system. Without conservation of energy, those mutual inductances wouldn't necessarily have to be the same, but we know that this is the conservative system, and however much energy we put in is the only energy that we have available. So in order for it to be conserved, those mutual inductances between those two coils have to be equal regardless of which one is acting as the source and which one is receiving the flux. Okay, so Let's see what we're looking for. Mutual inductance seen between the windings. All right. So we've got our little magnetic circuit drawn. So I guess the best thing for us to do right now would be to figure out what all of those reluctances are for the time being, right? So we were told to use the dimensions given in class. I really wish I had my notes in front of me so I could see which dimensions correspond to what things. So I'm just gonna write some things down here that I have. Okay, so first, let me do this in black. So the number of turns in coil A, which we don't particularly need, is 100. The number of turns in coil B is 200. The number of turns in coil C was 500. Our core permeability was 5,000 mu naught. The length of our gap was 1 centimeter. And now I'm trying to figure out what all these other lengths correspond to here. So give me just a second. So I believe that this length right here is what I'm going to call L1, where L1 is 60 centimeters. And this length right here is going to be L2, where L2 is going to be 40 centimeters. And then my width W there. And this guy should also be W, is 5 centimeters. Sorry, I have one more dimension here, L3, and I'm trying to figure out what it would be just based on my MathCAD sheet right here. This guy right here. Okay, let's put L3 here as 10 centimeters. Okay. So that seems appropriate enough to me. We'll go with that, and if my numbers are different, it's because we chose a different dimension, but it'll be fine. Okay. Oh, thank you. Yes, the thickness is 5 centimeters. We will definitely need that for our area calculations. Thank you for that. Okay, so let's work on finding some of these reluctances here. So let's work on the left one first, which that's fairly straightforward. So what should the total length of the left one be? So there's going to be a portion of it that is L2 minus W, absolutely, right? So that's this guy, this bit on the left here. All right, so L2 minus W looks like 35 centimeters. Let's start there, right? And then we've got this guy right here, and there's going to be two of those, so we'll sort that out. So I think this would be half of
L1
L1.
or minus 2.5.
Yeah. So half of L1 would be 30 minus 2.5 would be
27.5.
27.5 centimeters. And then there's going to be two of those guys. Okay.
One half.
Okay, sure. So yeah, so 55 either way. So 55 plus 35 is 90. Does that sound right? You guys have calculators? 55 and 35. So 90 centimeters. And then we're going to have 5,000 mu naught. And then we're going to have our area, which is 5 centimeters by 5 centimeters. So I'm just going to write this as 25 centimeters squared. All right, so 90 over 5,000 times 4 pi times 10 to the minus 9 times 25. And I got 5.7295 times 10 to the 4 amp turns per Weber. Now, should be pretty easy to see just by direct observation that R right is the exact same thing. Anybody have any beef with that? Probably isn't, but I either made a mistake there or we made a mistake here. So which one did we make a mistake on? Yeah. So for what it's worth, when I'm looking at my solution right here, because I see where I have 5.411 times 10 to the 4, I broke it down into a top left, a left, and portion and all of that kind of good stuff. So when I'm looking at my top left thing, I have 1/2 L1 minus a whole W, which actually doesn't make sense to me. It should be 1/2 of an L1 minus half of a W. So I think that's why it's slightly off, as I had an error in my thing. So we'll do it correctly here for what it's worth. That does mean that our answer right here is going to be a little bit off because it was based on the erroneous reluctance, but it's not going to be hugely off. All right, so I feel like we got the left side done pretty easily, and as I said, our right should be literally the exact same thing because it has the exact same dimensions. It's just the mirrored copy of that on the right-hand side. Are we okay with just looking at that and saying that's the same? Okay. So now let's do the middle. So what is our total length for the middle? Well, it looks like it should be L2 minus the W minus the gap, and we're good to go. So I don't know that L3 was even needed if we use it, approach it that way. So I'm saying that we have a total length of L2 from here to here. Then we would take away half a W on each side to get us the distance from here to here. and then we subtract the gap. Right? So that would be 40 minus 5 minus the gap. So 40 minus 6 is 34 centimeters. Are we okay with that? Does that logic make sense? So I'm going to annotate these things just so that for posterity's sake, I guess. So that is L2 minus W plus twice half L1 minus half W. This guy right here is L2 minus W minus LG. So 40 minus 5 minus 1. Our core permeability is still 5,000 mu naught, so 4 pi times 10 to the minus 9 henries per centimeter. Our area is still 25 centimeters squared. So 34 over 5,000 times 4 pi times 10 to the minus 9 times 25. And I get 2.1645 change times 10 to the 4 amp turns per Weber. And for my gap length is 1 centimeter. My permeability is 4 pi times 10 to the minus 9 henries per centimeter. And my area is going to be 5 plus 1 times 5 plus 1. So that's going to be 36 centimeters squared. I'm just going to make a note here. That's just LG. And this is W plus LG times T plus LG. Just so that we're all on the same page as to where those numbers came from. So 1 over 4 pi times 10 to the minus 9 times 36 gives me 2.21049 times 10 to the 1, 2, 3, 4, 5, 6 amp turns per Weber. So why do we add that extra bit of area? Or why do we add that extra bit of length to each dimension, I guess would be a better way to phrase that. So let me draw a picture for you. We covered this in one of the lectures, but that's okay. So if we look at our core material, when we have an air gap present, and this is an exaggerated representation, right? So I'm going to do my core path in this blue color that I've been doing, right? So straight through the center, it's going to flow directly through, no problem. But as we get away from the center, effectively what this air gap is allowing to happen is for our flux or our magnetic field lines to kind of spread out. So we're going to have something like this over here. Same thing on this side. And so because these fringing fields effectively see a larger area because the core no longer confines them into that finite space. We have to take into account that it's spreading out. So in the air gap, our flux path sees a larger cross-sectional area. And the general rule of thumb is just to add the length of the gap to each of the core dimensions to take that into account. So effectively, if this area right here represents the width of the core, then this total area right here, or excuse me, distance right here, we would treat as the width of the core plus LG. And the same thing, we would do the exact same thing for the thickness dimension. So we need to increase the overall area that the flux sees when it passes through the air gap because it spreads out to some extent. And this is just the general rule of thumb to take that increase in area into account. Is that a sufficient explanation, Brock?
I think, doesn't it mean that if you increase the length of the gap, like significantly, like increase it to like 100, almost like 100 centimeters, even meters, then wouldn't that make the resistance technically smaller?
Wouldn't that make the reluctance smaller? No, it'll make it. So let's look at things really quickly here. Okay. I see what you're saying there. So if we made the area larger, that makes the reluctance smaller. Okay, so I understand that, but you also have to take into account that the permeability of the air gap is much, order of thousands lower than the permeability of the core material. Also, we also have an assumption in here, effectively, that the length of our gap needs to be significantly smaller than the length of the leg that contains the gap, right? So this total length of this leg is 40 centimeters, and we have a 1 centimeter gap, right? So it is significantly smaller. What you're suggesting is essentially, what if we just cut this guy off here and let this whole thing be the gap? I would argue, why would the flux ever take that path? Right. Right. So again, that math is working under the assumption that the length of the gap is small as compared to the length of that flux path, right? So if the length of the gap is the whole flux path, it doesn't take that path. It's effectively just like an open circuit we would see in an electrical circuit. Okay. Okay, so this is where I'm running into a problem of my memory is garbage and I don't have my equations for mutual inductance in front of me. So I'm trying to remember what my expressions for mutual inductance should be. Because I can find that flux phi BC here using Ohm's law for magnetic circuits and what is essentially flux division, but I'm trying to remember to do, or what to do after that point. Anybody who watched the videos, can you remember any equations for mutual inductance? Yep, that'd be,
By saying the wrong
okay.
thing. This is that's the inductance, that's.
People in the classroom address are wondering what's happening.
So let me just write this down really quickly. So flux linkage through a particular coil is N1 times phi total, where this would be N1 times phi 1 plus phi 2, or N1. Penmanship is so bad.
I know.
So if I look at this thing right here, that looks like mu naught
Eight,
A,
area of the gap,
right? But if,
yeah.
so N1 squared over reluctance seen by coil 1 is, I think, what that is, plus
Did you take them? Were you able to help?
For me?
Mhm.
Shit, I mean, I took them, but you know, I didn't make it.
let me hold on to this for a second. I think I can figure it out. Yep. All right. Okay.
Never getting the dirt back.
All right. So we have all of these constituent parts and all of that kind of stuff here. So let's go through and figure out what this flux thing is going to be. Okay. So the way that I would do this, just looking at this thing, as I mentioned a couple of moments ago, would be probably using some sort of flux division. Okay. So I'm trying to decide if that would be like a current division thing, which would definitely be one way to do it, or a voltage division and Ohm's law kind of thing, right? This is the problem with circuits, is there's always more than one way to do things. So let's talk our way through this just really quickly, right? So realistically, I could find the total reluctance seen by our MMF source, MMFB, right? To find the flux, just for what it's worth. So I would call this guy right here phi BB. So that's the flux generated by coil B that's passing through coil B. And then I could find out how much splits off by applying what is effectively current division to this network or flux division to this network. An alternative thing that I could do, and it looks like this is the approach that I've taken in the last couple of times that I've taught this class, was to effectively find the equivalent MMF drop across these two parallel branches, and then divide that MMF by the reluctance of the right-hand path to just find the flux that's flowing through the right-hand path. Both of those results, or both of those processes, should give us the exact same results. So just for the sake of this is not the way that I did it in the video, so you'll see a different way. Let's do the flux division approach, okay, just for shits and giggles here. Okay. So what would our total reluctance be? Let's start there. So what is the reluctance seen by coil B? Okay, so R left in series with the parallel combination. So let's write this as R mid plus R gap times R right over R mid plus R gap plus R right. We'll just leave things symbolic for now, right? We won't worry about the numbers. We're just going through a process here. So are we all okay that that's what REQ or our equivalent reluctance would be? Let's start there. Okay, so just the left-hand path in series with those two other paths in parallel. Just looking at this thing and treating it like resistors, that seems fairly legit, okay? So the flux, God, that looks shitty, that I have drawn as phi BB would then be simply whatever MMFB is divided by that equivalent reluctance. Are you okay with that? That's just good old Ohm's law, okay? So now we would do phi BC using current division, which would just be phi BB times. So realistically, I could write this as 1 over R right over 1 over R mid plus R gap plus 1 over R right, like so. That's a little gross. So instead, I'm going to choose to express that ratio as whatever phi BB is times R mid plus R gap. Goodness gracious, my penmanship is getting away from me. Over R mid plus R gap plus R right. All that is me applying current division for two paths in parallel. Okay. So that's our flux. Our mutual inductance so let me see if I can add a page here. Edit. page. End page. Just a blank page. Okay, good. Okay, so looking at Sam's notes here for just basic relationships. Flux linkage in general is just the number of turns times the amount of flux, right? So the flux linkage through coil C would be the number of turns in coil C multiplied by the flux flowing through coil C. And our mutual inductance is simply our flux linkage divided by our current. So we have enough information to get phi BC based on things, or we don't actually have quite enough information because we've got things in terms of MMFB that we don't actually know. But that's a good thing because it's going to wind up canceling out here in a moment. So let me explain what I mean by that specifically. How did we find current IB previously? Right, so this is just a quick aside over here. So in the last problem that we worked, if I'm remembering correctly, we had something like MMFB would have been equal to NB times IB, and that would have been the same as phi B. So B is equal to I times REQ, right? So IB would be phi BB REQ over NB. Are you guys okay with that? Okay. So let's substitute some things in here and see what shakes out. And again, this is an entirely different way that I've done it before, but I strongly feel that it's going to wind up coming out correctly here. So we would have NC, I'm just going to leave this as phi BC for right now, over IB. Well, IB is phi BB times REQ over NB. So that's just going to put an NB in my numerator. Okay. So I have NB times NC times phi BC over phi BB times REQ. Let's keep on substituting things in here. Okay. So let's start with, I'm just going to put this NC times NB here to the outside. Okay. Phi BC was phi BB times R mid plus R gap over R mid plus R gap plus R right. Phi BB by itself, these guys wind up canceling each other out, which is great because we don't know what the MMF is, and this is what gets us away from having to need to actually know that, divided by REQ, okay? Where we could put REQ as R left plus R mid plus R gap times R right divided by R mid plus R gap plus R right. Close this bracket off. Okay. So what I'm going to do just real quick like here. Let's call this thing, just for shits and giggles, X. Okay. So that our mutual inductance, MBC, comes out to be NB times NC. X, which is just some ratio of reluctances, over R left plus, so notice that we have a factor of R mid plus R gap over R mid plus R gap plus R right in this guy right here. So this is literally just X times R right. Now I'm going to take things one step further, go away thing. Oh, good God, not whatever the hell that was, don't do that. So we know that R left and R right are the same thing. So this is going to look like NB times NC times X over R left times 1 plus X. And now we literally just need to substitute in numbers and we're done. So for what it's worth, let's go ahead and figure out what X is. So that's R mid plus R gap. Sure. I'll do whatever you want, Zach. I don't need to give you all A's. You'll earn them.
Okay,
You guys are.
Read all that.
I like, you're trying to steal my grader's job. That's how I see it. Or, well, not steal it, just make her.
I'm sure they'd appreciate, let's work on their table.
No, I feel like they want to make money because I'm not gonna pay them for doing nothing.
I mean, you don't pay them.
What's that?
Those grades pay them? Crazy.
For some people,
Oh.
it's because the school doesn't pay people nearly enough money as far as I'm concerned.
That I'm guaranteed. School thinks that. Schools don't think that the lowest currency is peanuts. I like it.
Oh my goodness. All right. So I'm just trying to figure out what the hell this this X thing is. So it's mid plus gap. So let me just do this in little parts here. So 2.1645 times 10 to the 4 plus 2.21049 times 10 to the 6th. Make sure I put the 6 there. I did. Okay. All right. So it's that thing. Let me just store that as A. And so then it's going to be A divided by, sorry, this is taking me so long, A plus R left, which was 5.7295 times 10 to the 4. So I got X to be 0.97497 and some change, and I'm just gonna store that as B because I'm lazy. Okay. So let's see here. So NB was 200 times NC was 500 times what I have stored as X divided by R left, which was 5.7295 times 10 to the 4 times 1 plus X. So this comes out to be 0.861618 henries, or 861.62 millihenries. I'll be damned if that isn't real close, using an entirely different approach to the ones that I've used previously, just to show you, and also to see if I could, but show you there's different ways to approach this.
I thought we were just doing this for fun.
A little bit of A, a little bit of B.
You can go back down to the answer room.
Sure. Thank you, Sam, for allowing me to borrow your notes to remind myself of what the hell I'm supposed to be doing in this class. Fair enough.
I'm glad you can make sense. Oh, yeah. No, that's fine. I'm glad. you
Yes,
can
ma'am.
make sense.
All right, 2 minutes, good.
Mhm.
Test tomorrow on your, not tomorrow, Thursday.
Thursday.
Oh, yeah, that's definitely not happening. Yeah, for sure.
Every time you're like, put an exam on Thursday, I was like, Dr. Herman is not gonna do that exam. That is not happening.
So, okay, so let's talk about some things really quickly, okay? So we are a couple of lectures behind at this point for my illness and also me just getting distracted with things. All right. So we need to talk about in our next class meeting, the practical transformer model. So we've done a bunch of work here, kind of understanding things about how mutual inductance and all that kind of good stuff shapes out. Or let me rephrase that. I have attempted to explain how mutual inductance works, and you guys have probably gotten frustrated and just said, fuck it, but that's okay. So now we're going to talk specifically about transformers for 1 to 2 class meetings, where we are going to develop what's called a practical transformer model that takes into account all of the various loss mechanisms that we will see. So, for instance, our transformers will have real wires, which means that we will see ohmic losses. Our transformers will have opportunities for flux to leak. So we will have some inductances that take into account flux leakage. We have a core that has to be magnetized, and the magnetization of that core causes it to heat up. So we'll have some heat losses in our core. We'll also have a core inductance, which is literally just a way to kind of represent what's going on with, actually, sorry, the heat losses are from eddy currents and the inductance is from magnetizing the core. My apologies. Then we'll have some things on the secondary side of the transformer as well. So we're going to have a kind of gross-ish looking circuit model for a transformer, probably by the end of the class on Thursday. And then our next meeting will be about simplifying that model based on practical observations about the magnetization current for the core is so much less than the current in the primary winding. So maybe we can kind of shuffle things around a little bit, and we're actually going to wind up with a transformer model, circuit model that doesn't contain a transformer, which actually is a good thing because we don't have to worry about relationships for stepping things up and stepping things down, and remembering that the current follows the inverse relationship of the voltage and all of that kind of good stuff. And then that will be the end of the material for exam 1. So realistically, we would be looking at the earliest possible date for our first exam would be not this Thursday, but the following Thursday.